Great. Thank you, everyone, for joining us for our third talk of the spring seminar series of Design++. Tonight, yes, we're happy to welcome Professor Andrea Frangi. Before I introduce him as a speaker, I will briefly share with you an overview of the seminar series for this semester. As I said, this is the third talk, and we have our last one in about 2 weeks. So if you happen to miss one of the talks that you might find interesting, you could also find an archive of all of the talks that we have had in the past. For those who are interested in looking at the talks, you can look on our YouTube channel. And last but not least, I would like to introduce our speaker for tonight. Professor Andrea Frangi will speak about emerging innovations in structural timber engineering. The talk presents an overview of around 15 years of research activities of the Chair of Timber Structures here at ETH Zurich. We're also very happy to welcome Professor Frangi and his team as a new member of the affiliated faculty network. So thank you very much for also sharing your insights with our community. So this is a nice way to initiate discussions and exchange within the network. So as some of you might know, Professor Frangi is Professor for Timber Structures at the Institute of Structural Engineering here at ETH Zurich since 2010. He is also actively involved and heading numerous code and standard committees. And so looking at the list, I will not include all of them. But there's Eurocode, SIA, and topics ranging from timber and fire safety. So with that, I would really like to thank you and introduce you for the evening.
Thank you very much. Also, not only for the invitation, also for the trust, also for accepting us in the Design++ family. And yes, as you mentioned, I will try to give you a short overview of what we have done in the last year, starting maybe with the current photo of the group. I have some time to count the people. We are 21 at the moment, with 12 Ph.D. students, and the chair was founded 2010. Yes, we started with few people, as usually, with 4 people for a Ph.D. student. And you see now in the last year we are around 20 people. So it's already a big group, as you can imagine, but with PhD student, postdoc, with the support also from some colleagues from Tampa, I think it was able until now to manage the group. Yes, I think it's also maybe showing timber is becoming important. Mission is very simple, of course. We are at ETH, we want to educate our students for the highest level in timber structural engineering, but of course also to develop fundamental knowledge, more in the basic research, but also innovative structure in the applied research, and also my involvement in standardization. I think it's also important to transfer this knowledge to code, to standard, and to help, of course, the industry with consultancy and with solution. In the education, when I was studying at ETH, going back to 1995, there was only one lecture on timber. And now at least we are doing 3 times more. We are teaching at the master level at the department of Civil Environmental and Geomatics, and we are offering timber structure 1, 2, 3. We have also the fire safety and acoustic engineering, which is also offering the Master of Integrated Building System. We offer, of course, project work, master thesis, building structure is nothing with timber. It's another lecture that I'm doing, and yes, maybe you know, I'm from Ticino. I'm happy to still be there 6 times per year at the academia teaching steel and timber structure. I have to say, maybe it's difficult to say if this is many or not so many. I can tell you when we have done 24 master in one semester was 2 full days. But you can imagine, we don't have 300 students. We have maybe 60 students. And if 20 are choosing doing the master, it's probably because many people are saying they want to do the master because we are doing timber. So they are really attracted by the material timber. Then, of course, maybe during this period, there was maybe also the change from Peter Marty to Walter Kaufmann, Fontana, Taras. So this big group are a little smaller, and we profit maybe a little also from this particular situation. We have 3 pillars: the basic research, the applied research, and FIRE. I will try to go through these 3 pillars and showing you what we have done in these 3 pillars. This is our history. Actually, usually this is for me the most important slide, because what I show you is the work of these people. It's not my work. We were able to finish from 2010 up to now 27 PhD work in the different area. You see the color are showing you in which area, the basic research, the applied research, and the fire safety. Of course, it's nice if some of these students are now professors in some other university. Most of the other doctors are working in the engineering office. Most of them are here in Zurich. Probably most of them were here during the contact treffen today, trying to recruit in possible engineers. Yes, I start with fire safety because, of course, fire safety was the main killer criteria. We were not able to build timber building due to the fire safety regulation. This was recognized also by the timber industry. And yes, now you see Mario Fontana here. He was professor at ETH from 92 to 2019. And he started in 92 what we call the fire safety research at ETH. Now you see here, I was the second PhD student by Mario Fontana from 95 to 2001. The first one doing the PhD in the area of fire and timber. And then there were two PhD by Mario, and then from here are my PhD when I took over the fire safety from Mario. What we have done is just burning. So we have tested all possible wall element, floor element. We have done this kind of compartment fire test. This was just important to get the knowledge and to bring the knowledge also to calculation model. And then, of course, to do this together with the industry. But the most important thing in all this process, the Fire Safety Authority was directly involved. At the end, this was just build up a trust between industry, authority, and the institute involved. Yeah, and of course we focus on different topics. The topic of what is the influence of the adhesive. Here, Miriam, this was Michael Klippel thesis. Miriam clients focus more on the CLT panel with the beam. Pedro Palma was, of course, we always have to combine element with connection, the fire resistance of connection. Reto Farni was the first person doing really a code calibration for the new Eurocode for the design of timber in fire. And I mean, all this work, not only done here at IBK, but worldwide, were very important because maybe you know the revolution in the timber industry is dated 1st January 2005, when the new regulation allowed to go from the 2-story to 6-story. So really, going to the medium-rise building. And now with the current regulation, 2015, there are no more limits actually for timber. And for the new one coming now in 27, the situation will remain the same. From the fire safety regulation, we have the best one worldwide. You can do what you want, actually. So, but we have to do the right things, of course. But now you see in Switzerland, we have 20 years of medium-rise building. This is really, and it's not the chalet in the mountain, it's also in the city of Zürich, Winterthur, Basel, everywhere. Now you see this kind of building. I think for me, state of the art, honestly, this kind of building we should do more or less in hybrid or in timber. It's really what we can do. Easily. And then, of course, now you see this resonance. We have the tall building like the Zwart. We have maybe the nice structure, or Swatch, Elefantenhaus. There are the first crossing wild bridges in Switzerland. And maybe you know that the new dock at the airport will be also done with timber. So 2030, when you land in Zurich, let's see what's happened in the next year, but theoretically there will be also a new airport made in timber. I think actually it is a nice period. But this kind of structure open also very important question. Is not anymore the single family house. When we are doing tall building with timber, there were important questions about should we really stay with the framework of fire resistance, or we have to go even a step forward. And actually already 26 years ago, we recognized, and when you do a fire test with a compartment and everything is made of timber in comparison to a compartment where you protect timber with gypsum plasterboard, you see the photos is showing that the fire dynamics is completely different. Here we have much more combustible material. The flaming outside is much higher, is stronger. So there is, of course, everyone knows if I put more combustible material, we change the fire dynamics. And this is done also now worldwide, many tests asking for maybe new solution. And this is now where we are doing in the last year, especially with the Ph.D. of Jochen Schmidt and Fernando, where we focus really on the real fire behavior. We developed this special device. It's the fire apparatus for non-standard heating and char investigation. It's a long channel. We have a quick response heat panel. On this balance, we place a small piece of timber, and then we can expose the timber to different heat flux. And at the same time, we can play with the most important other parameter, temperature and air. How much air we bring to the timber surface, because you know when you are, if you want to accelerate the chimney, you just start blowing air and so on. Air is an important parameter. And now Jochen Schmidt developed this TIX model, is the timber charring and heat storage. It's the first time that we have now a model which is able to consider the influence of this additional CLT element, but also we are able to consider the positive influence of the char layer. Usually we focus on the timber because it's our load-bearing element. But the char layer is so important because it's protecting the timber, and because the char layer, you see, it's like a battery. It can store heat. This is the reason because we are using charring for the barbecue. It takes the heat and it gives us the heat over many hours and so on. And now we want to understand better how much heat can we store in the char. But then there is another issue, and this was also studied by Schmidt. The char is combust during the fire, especially in the cooling phase. When you introduce fresh air, you start oxidizing. So the char is starting disappearing, meaning that in this phase is storing heat, but then later on is releasing heat. So then we have now the possibility to model also really the storage of the heat in the char, but also, especially in the cooling phase, the release of the heat due to the combustion of the char layer. Then we extend also the model with the so-called falling off, and the char is combusting on the floor, and again release more heat, and we are able to estimate also this contribution. We are lucky that now we have a fantastic device here at ETH, the fire simulator. After the fire lab at the EMPA was closed, for us was a disaster, but we were able really to get this new device here at ETH. It's a small, it's 1 meter by 2 meter, but it's so designed that we can even do this kind of bending test with glulam beam. And then the most important feature of the fire simulator is not only we can simulate any kind of temperature development, this is the reason we are calling simulator, it's not a normal furnace, but we have a special device, we can also adjust the oxygen content. So we can really simulate a real fire when at the beginning, when you have this so-called flashover, now everyone knows what is flashover after Grand Montana, when the whole compartment is burning, usually you don't have any more oxygen, and in the cooling phase, we are bringing more oxygen, and we are changing also the fire dynamics. And we can really simulate in the fire simulator this kind of real scenario. So I think we will have now really the best device to continue the research. Now, important is always the characterization of the residual cross-section. 30 years ago, I was just doing by hand, and yeah. And now we are doing with this kind of very simple, you take some photos, you create a 3D model with Autodesk Recap photo software, and then you use a MATLAB script, and at the end you get a perfect 3D visualization. So I always say to the PhD student, oh, if I would have these tools 30 years ago. And now, of course, now with your help, we replace, as far as I know, Photos, Recap, MATLAB. There is the Artec Leo 3D software, and you get this kind of image. And I mean, this is amazing. Because at my time, I was just able maybe to have a beam to cut. I have only 3 cross-section. And now I have the full picture of the beam, of the plate. You can imagine what we can do nowadays. And Fernando Perez was not only interested maybe to residual cross-section, he is doing tests with so small pieces of char, because he is characterizing the thermal property of the char layer. And yeah, I mean, you cannot believe how accuracy is now this image with the reality. Jamit was also helping, but this is more a side project with Bastler Hoffman, using Revit to generate fire design plan. I think this is also the future, to check the fire safety plan, to check the evacuation is now so easy. You give me, and for me it's everything new, but it's, I think, very fascinating, because you can theoretically try to simulate, to really see if evacuation would work as expected by maybe drawing to the plane. Going to the basic research, at the beginning we focused more on glulam. It was more about grading better the material, characterization of the material. There was the topic about stability, the topic about beam with notches, with all. So these are typical basic research, improving calculation model, going to SEA standard, Eurocode. But nowadays we are moving more from this, I design element by element, beam, column, to more this system-based design concept. We consider the whole structure. And for this, we introduce more this scale approach. So we are looking at the problem going from the material to the system, going through fastener, element, assembly. Of course, for each scale, we try to have a mechanical, physical model. With this model, you can always propagate some uncertainty and always see to connect the different scale. And I think this scale approach is very interesting to understand where we have the problem. Sometimes maybe we are focusing too much on this level and the problem is on this level, or vice versa. And sometimes we are doing something only because we have the instrument, we are strong in this field, but we are neglecting maybe that the problem is at another level. And now we are trying to work in all projects using this scale approach. Now we are building with softwood, so mainly spruce, but we have an increase in also hardwood, especially beech in Switzerland. So some years ago, of course, we got funding from BAFU, and we have done a lot of research in hardwood, developing the glue made of beech, also ash, Forticino, even chestnut. It's always beam and connection, because without connection you cannot do anything. Here you see more the typical connection with slot and strip bait and strip dowel. Also this connection work in beech, but we have to design a different way. Then there is our super beech, the LVL, the laminate veneer lumber. This product has fantastic property. Then it's like our C200 for concrete maybe, or S1000 for steel, because we go from 30 megapascal to 80 megapascal strength. And for this material, we have done also some interesting research. Of course, we are also trying sometimes to solve the problem of timber as a natural material by introducing maybe fiber. It's always a dilemma, huh? We introduce fiber, yes, we improve something, but maybe we are not so good with other things. But having fiber, of course, you can solve the problem of the knot on the tensile side. The tensile side is not anymore governing. You can even have a ductile behavior, so a beam which would fail brittle with the fiber is behaving more or less like a steel beam, because then you create first the failure on the compressive side, and timber in compression is still, you get some ductility. But of course, we have to introduce some fiber. You will see later on some other application. This is one of the last projects that we finished. This is a typical project together also with the industry. There is this kind of light timber frame with opening, and there were no rule for designing with the opening, and now we provide this rule. These really are a current project founded by SNF. I would like to mention, of course, our first project together with Gramazio Kohler. You see the idea to build in the future this tortu with CLT plate, any kind of folded structure. Of course, on our chair is more the connection. On the chair of Gramazio Kohler, there are more interesting things in the digitalization and so on. And yeah, I think this is, of course, a very interesting project. We also are discovering, and again, also thanks to the collaboration with Gramazio Kohler and with the CNC machine, we are able also to do maybe some more research in the timber-to-timber connection. Without steel part, there is a renaissance also for this kind of connection, and we have also a project ongoing. This is something special. This is maybe something unique. We have a PhD student coming from Bhutan. And Bhutan is a country with 70% of forest, and they are not using anything of they are just maybe taking some logs and bringing to India, and now Chewan is trying really to develop the simple grading rule just to be able to characterize the material of Bhutan, and of course in the future they would like to use the material and not just maybe cutting some tree and exporting to other countries. Now moving to the applied research, what we call the innovative timber structure. Usually our most industry's project together with industry. We go to industry because we have an idea, or industry is coming to us, we have an idea, can you help us? Yes, this is already one of the first projects, the post-tension timber frame solution. It's a very simple idea. You have continuous column. You have two beams which are connected to the column just because you have a post-tension cable going through. And of course, we have done many tests. It's worked really in a nicely way. It's a self-centering system. You don't need additional steel element. Of course, now we have the problem. The column is loaded perpendicular to the grain. What we do, we switch from softwood, this is spruce, to hardwood, beech or ash. So we just take a material which has better mechanical properties. Yeah, we have done two PhD students. Jelena was more looking at the horizontal stabilization with the post-tension frame. This is what we do in the Bauhalle. In scale 1 to 4, a 2-frame, 2-base. We simulate a typical earthquake in Italy. So just the frame is just shaking, and after the seismic is going back to the original position. The idea is not in Switzerland, we don't have really high seismicity. It's maybe interesting also for other countries. For us was the idea to have a beam column connection without steel, just a post-tension cable going through. Then with the beech LVL, we developed this timber concrete composite. This was more like a present for the concrete industry. They always need a formwork. We say take this 4 centimeter beech, but this is also replacing the steel reinforcement in the concrete. And luckily, we were able to build the House of Natural Resources. It's now 11 years ago, inauguration 2015. Built around 2012 up to 2015. You see also other professorship involved, Ingo Burger, Arno Schlüter, Eleni Katzi. And I really think, of course, now we have Artec Lab, but it's a small, nice building. Probably it's the first real living lab that we have built at the campus, because we have built new technology. Nobody has done this previously, and of course we are measuring everything for the last 11 years. So we know everything. It's not that we are measuring many things because the building is performing well, but still we were able to do something unique, thanks also to ETH. So doing tests during the construction phase, of course it's about dynamic behavior and so on. Jumping on slab, shaking with the shaker, with the hammer. And the unique thing we were able even to do in the different construction phase. Only the frame plus floor, finished building. That was only possible because, of course, ETH was allowing us, and of course we hope that now with the living lab, the next one in Ile, we can repeat. Of course, it's not 20 meter by 20 meter, it's a little larger, but I think it's a unique opportunity also to compare numerical model with real things. And what we have, for example, is 11 years of the post-tension force, because this building has a post-tension frame. Now we know that after 11 years, we lost around 15% maximum of the post-tension force. And we are very happy because it seems that now we are reaching a plateau. We don't have to post-tension the cable. We are really in a very good situation. Post-tension, for me, is very interesting, especially for the large span. Here you see a project for this crossing wild bridge in Coppingen. Now is finished, and Astra allow us to really test in mock-up 1-to-1 this composite beam with the post engine, just to be sure then later on it worked. Was a very nice small project. We have been actually supporting especially the engineers. And another one that is for the new sport centrum in Oerlikon here in the city of Zurich. There are again very loaded glulam beam, 46 meter span, and in order to meet the requirement, the formation and so on, it is planned to have post-tension cable. We have done the different tests for the engineers just to have more knowledge. We are doing a lot of timber in combination with other material. My PhD was on timber concrete composite, so it's normal that I have this kind of combination also in my background. And here you see now what we call the micro notches, developed by Katharina Müller. It's very easy, you cut not deep notches. It's very thin, only 4 millimeter notches. It's like a shark. This you see, the company called a shark, not micro notches. But it's enough, this interlocking, to transfer the shear force. And we are very proud. Katharina is now implementing the slab with a small spin-off. And she's doing many square meters. So it's the best what we can do at ETH, develop something, and young people are bringing this into the market. We have developed also a glued solution. It's always a delicate topic, should we glue concrete with timber? This was done together with Sika, with Ingo Burger, EMPA ETH, with Fagus. It worked. We are able even to have a glued solution. Of course, you have the best connection in terms of stiffness, but maybe we are losing all the possibility of ductility. For the ZWAT building, because in ZWAT building there are timber concrete composite with the beach and the concrete. This was also a premiere. Usually Erne is using softwood, spruce, and because they switched to Stabschichtholz in Buche, in the beach Fagus product, we have done, of course, the characterization with push-out test. We have also a mock-up. But by switching from softwood to beech, by keeping, however, the same rules for softwood, you are on the safe side, usually, and we are on the safe side. But in the future, we can even use. Timber structure 3 is the crazy idea to glue the CLT plate in this way. Nobody was believing it is possible. After 20 years of research, it worked. It's also the company on the market. They are doing many projects. CLT is using a lot of wood. We always say we should actually use less wood, build more with less wood. And this is the reason that in a follow-up project, we try to replace the CLT with the hollow core flat slab. So having a plate and the web and the plate, these kind of hollow core timber elements are much more sustainable because we use half of the material. But of course, then you need a company that is able to produce this and so on. So at the moment, CLT is the most important product, but I think in the future, probably we will also go back to this kind of product. In another project, the timber concrete composite biaxial, these are also pure timber element working in two directions. And in this project, we also develop a timber concrete composite working in two directions. Usually, timber is working more unidirectional. But I think in some situations, it's really interesting to have this biaxial function as you have with the normal flat steel reinforcing concrete flat slab. And yes, it's more a sandwich where you have a timber board, the concrete is on top. Then we need this steel cylinder to connect the element. Again, we are really using maybe 8 centimeter concrete, 6 centimeter timber. So we are really using less material, but having a very high performance. If this P tower will be built, we still hope that our system will be implemented in the project. The P should be actually a lighthouse project because it will be a tube-in-tube system, a pure timber structure. We have also developed it together and done also the test. It's a frame construction, beam, column connecting together, moment resistance. This is the test in scale 1:1. If you want to build 80 meters, is what you need. In beach LVL, it seems really be able to go up to this height. Now I have called another TCC. Currently we have with Erne, again, we are developing another timber concrete composite. With, for Erne, amazing idea, they prefabricate a concrete element. You take the beam, you place the prefabricated concrete element, then you fill this gap. After 24 hours, the element is ready. I think it will work, but it's something very interesting. And again, you see another one with another company, but this is more the CLT and the concrete biaxial with the micro notches, however, not with the deep notches. So I think that TCC will be really an interesting combination of these two materials. Now I have to mention, of course, because this is really a huge project, the Inno-Swiss flagship, Think Earth, where we are now trying to combine timber with clay. We invented this mathematical error, 1 + 1 is 3, so we really think that by combining these two materials we have added value and we can compensate especially the weak point of timber. We don't have thermal mass, sound insulation, or even fire safety. With the clay, we have done the midterm review the last week. After 2 years, I think really the project is running very well. We have actually 10 projects together, and some are more dedicated to the earth-based material, some more to timber, and then we combine the material together. We will see in 3 years where we are. Now, this tall timber building competition worldwide is, of course, interesting for us because each city wants to build 1 meter higher tall building. But this raises again more questions about stabilization, about robustness, about also moment resistant connection. And with Aurélien, now we have studied what is the possible height that we can reach with a pure timber structure. If we have a frame structure, if we have a tube-in-tube structure, and what we can do, of course, now we are simulating building with frame structure. Governing by tall building usually is the wind design, the peak acceleration, the peak displacement, and usually the structural safety is not so important. And we study different structural systems, the frame, the tube-in-tube system. Of course, nowadays with the supercomputer, you can run 2,000 simulations per configuration. And now we are able to understand first on which level can we reach, and we think we can go up to 150 meters with tube-in-tube system. And especially we know the connection, this beam column connection, what is the demand? What is the performance of the connection required for this kind of frame action? Now, the good thing is that this young student, they are so happy also to go to other method. And Aurélien was now really training this autoencoder. So it is about this beam column connection with glued-in rods. Of course, first we developed the abacus model, check that, okay, when we have some input, we get the performance. Now we have a model then to validate also the autoencoder. As far as I understand, you would go first in this direction, you go in the other direction. For me, it was amazing when I see the autoencoder in comparison to the abacus, meaning we think abacus is the right solution. I mean, of course, chapeau. That's very interesting. For us, it's really good now to take this new opportunity because timber is you have so many uncertainty when we work with timber, with the properties and so on, that this kind of tool allows us maybe really to be more efficient and at the end to be more reliable. Now, we need this connection. We need, however, this. Aurélien is developing one connection with ETH. One connection is finished. It's the work by Charles Bink. He developed this beam column connection with this steel element, which are placed in the column, in the beam, and then you connect together only with these mounting bolts. And I have to say, with this idea, you can create any kind of connection, the cross, the beam column, the portal, or this kind of connection, or to attach a beam to another, or just beam to beam. Is just a brilliant idea. You always have the connection to the timber with glued-in rods or with screwed-in rods. And then you have just two steel parts which are matching together, male, female, self-centering. So you just bring your column, then you take your beam and you just place, and at the end you have 3 or 6 mounting bolts and you connect together. Yes, Charles finished already the work. You see now the final test with the cross in scale 1:1. And we tested 2 different solutions. This one is even more performing. And what we know is that this connection is able to, this would be, just look at this line, is the connection rigid. What we think it does not exist. If we would take steel and weld together, yes, we would follow this. But now with this connection, we have around 90% of the stiffness, which we know is more than enough. We have really a moment-resistant connection, which is even ductile in the failure. But for me, amazing is what happened after he has done the test. He destroyed the beam column, and in 5 minutes, he was dismantling the element. Just remove it, these bolts, and then, because now we are talking about circularity, reuse, dismantling. Of course, I don't want to say this is a solution, but this, I think, is an interesting solution, because with this kind of connection, also in 15 years, you can dismantle your element easily. Let's see, we are now trying to bring this to the market with a big company, not the red one, the other one. Let's see if we are able. I finish because I see time is running with the topic robustness, which is, yes, what's happened or what should not happen. If you have an auto crash that the building is collapses. This was Miami, also building collapses, the failure of a column in the garage bring to the failure to the whole structure. This is not war, this was the accident in Beirut, the explosion. And now we have other problem, unfortunately. But this is, we are working on this topic, because timber is prefabrication. We just connect all elements together. It's not concrete, it's monolithic, so we know that we are not so robust. And now you see, we started 10 years ago. I was thinking, oh, we do one PhD, the problem is solved. We have finished 2 PhD, we have 4 PhD ongoing, and I don't still see the end of the problem, which is much more complex. Konstantinos is set up a framework. You see again the scale approach, going from material to the system, just to be sure where we have the problem of robustness, at which level. Robustness, you can imagine, you have a probability that there is an exposure. This exposure can bring to a damage, and then we check if the damage is bringing to the collapse of the building. And we can even quantify the robustness with the robustness index nowadays. So we have also some tools. But of course now we need a model to start simulating a collapse of the building. We cannot build the building and try to see the progressive collapse. So we are going more to numerical simulation. Costantino has done the first step. Again, here we have the possibility to propagate many uncertainty through the model, and really trying to evaluate how a measure is robust or not. It's always a question when we are enough robust or not. But now with Alex Kauf, PhD, I have to say, he developed this collapse modeling framework with so many interesting features. We can even simulate elements which are failing, which are detaching, which are falling off and eating other element. So we are now really trying to have a super tool which is able to simulate a progressive collapse. That, of course, we have to validate with some tests. And some tests can be, for example, and we go back to the fiber. Now you see a glulam beam with fiber. Lucas Esser, what he's doing, if you take a simply supported beam and you load, you will have just a failure in bending. But if the beam is restrained at the end, we can activate the so-called catenary action. So you go from bending to tension. The problem is that usually in timber, before you go to the catenary action, you have the failure in bending. And now we are saying, okay, then we go back to our fiber. The fiber are reinforcing the tensile side. We have done with, again, with Ingo Burget, some small scale test. It seems promising. And then we decide, let's go to the real large scale. And we have done this large scale experiment. Again, we use the Baualle. We have the possibility with also digital image correlation to see things that we are not able to see in the past. But the most important thing is that we demonstrate at a large scale that when you have a beam which is actually restrained, this is the total force that we are taking, and we see at the beginning it's only working in bending, but by increasing the vertical deflection, we are really activating the tensile force. So is this, you see, from a certain deflection, we are going from the bending to the catenary action. And I think this can be an interesting application for the glulam with fiber. Otherwise, why I should introduce the fiber? But if you want to have maybe a beam which is not failing in tension and is activating catenary action, maybe we need this. Katharina Sroka is looking more at the connection. So the typical example, the column is failing, what happened in this connection. And here you see how we are doing the test. So just pushing this connection or this part and see how much we can really rotate the element. It is about, okay, ductility of the connection. You see large deformation. You see also large rotation. We have done now different tests with LVL, which is the homogeneous material, with glulam. Now just to cut a little the story, you see really in this test, at the beginning we have really a typical moment, but then by increasing the deformation, the moment is reduced and we activate really this axial force. So we were able really to demonstrate also this catenary action in the joint interconnection, which is good if we are able to activate this catenary action. Yes, I mean, we have now evidence that by activating catenary action, we can activate alternative load path also in timber engineering. For steel, concrete is easy, usually, to do this. And now we think also possibility for timber engineering. I finish with Joel and Montalbetti, which is the last one taking care or started in this topic. Collapse model, it will improve this. It is really in focusing on the rate-dependent behavior. When you have a car crashing into the column, you have a dynamic factor. And this is, this should be what happens when you have a car coming and not stopping. It's not coming, it's coming, it's not coming, I don't know. It's not important. You would just see the car crashing. Now, what is important for us? We know timber behave in this way, quasi-static. If we increase the velocity of the impact, the strain rate, if we have this dynamic effect, usually the stiffness is a little higher, but sometimes we assume the same stiffness, but we know that we will get higher strength. The question is how much? Is 10% more? Is 50% more? Is 100% more? We are interested in this dynamic strength increase factor. And for studying this, this was Alex, and then Joelle took over. We developed this pendulum test setup. It's around 4.5 meter high. Here you have 3.5 ton steel. You have many devices. The most important is the high-speed camera, taking 6,500 pictures per second. And what we are doing is something that everyone studied in primary school by pendulum, so an energy balance. You let the pendulum going, crashing into the timber, and without the timber come here, and with the timber stopped here, and is going back. So we are able to calculate the energy release by the impact. To calculate the force, we need the stiffness of the element, we know, and we have to understand the displacement. What is doing this beam? And I think Joelle is amazing. He's able to track the displacement of the beam by putting this Aruco marker on the beam. Then there is a reference point, and is able to follow the beam. And because also of the high-speed camera. And now by changing the angle where we start and also the length, we are able to do the test with different strain rate. And the results, first I show you if it's working, maybe a pendulum test. It's not starting. Let's see if we start in this way. Yes. So spectacular, yes, of course, the test is this. This is spectacular. What we see with the high-speed camera. That's incredible. You can spend hours, and of course, Joelle is spending hours. and we are even able to characterize the different okay, it seems that then let's continue in this. It's the last slide. We are even able to characterize the different failure mode and to quantify. So you see if it's a fiber, if a finger joints, usually it's a mix. So I think it's really fantastic what we can do. And now we have the dynamic strength increase factor. We are able for the first time to quantify with tests done in the large scale this factor. And based on the strain rate, yeah, we reach up to a factor 2. With the pendulum, we are simulating around a car crashing into a column, 40 kilometers per hour, something like this. Yes, I think I skip this one. This one, we still have many challenges, but we have many opportunities. I still have 10 years of ETH if everything is going well. So we will try to, yes, promote timber. And the vision would be the Empire State of Wood. We are happy if we do some more building with timber. Thank you very much for your attention. And I told Fabio I will finish after 45 minutes. Now it's 1 hour. Sorry to be so long. Thank you very much.
Thank you, Professor Frangi, for this excellent and comprehensive overview of the research in your chair. I think it's very instrumental in terms of pushing what's possible with wood structures. So I would like to first open to questions, if there are any in the audience. So, okay, there are a few people. I'll start with you.
Thank you very much for presentation. I have a very small question. Just I was curious from before, like since you showed the glue lamp beam for the passage of the bridge for the animals, yes. And then there is a glue lamp beam, and then below there is always like a hardwood that is probably glued below, and sometimes even a steel plate below. What is the key reason? Because fibers are crushing at the supports, and how do you size those elements? Like why it's like such a size, not a bigger one, not a smaller one, and the same for Hilti as well. Like you have like small pieces of steel, and then how do you dimension those elements? Like. Mm-hmm.
Yes, usually maybe we can discuss bilaterally exactly which example do you mean, but usually we introduce hardwood, especially you mentioned when we have a problem perpendicular to the grain. So with the post-beam construction for the honor was, of course, we have compression perpendicular to the grain. It can happen that when you have in the beam for the crossing bridge, there was no beach. I think maybe there is something that was not clear. This is a normal glue lamp made of softwood. The post tension is a straight cable. We have post tension parallel to the grain. We don't have any problem. Usually we switch to hardwood only when we load timber perpendicular to the grain, because then we get 3 times more capacity and so on. It can happen that on the support, again, for compression perpendicular to the grain, you introduce some hardwood. But maybe we can look at the slide, because maybe there is one slide which was not so clear. Thank you.
I have a question. Thank you very much. You showed many very innovative structural systems and material combinations with concrete and different types of fibers, and on the same slide, many of them are in real-world buildings currently built. There were logos of architecture firms. I was wondering, what is the usual typical workflow? Is this a product that you have and then architects reach out because they want to do something with it, or they are first and approach you to develop something, or what is the how is maybe in some of the examples how is that workflow going?
Yeah, I can tell you for all examples. By the House of Natural Resources, the post-beam construction, this was our idea, and we approached the company, Ehring, and asked, are you interested to develop this? I would say for the TS3 was the opposite, was more Stefan Zöllig approaching us, oh, we have this idea and so on, can we develop together? So it really in both directions. But we always, if we have an idea, we always try to, to have immediately a possible partner. Then there are some projects where we do the research and then we look for the partner, like the joint developed by Charles Pink. Actually, now we look for a possible partner. And I have to say, some innovation, thank you for saying most of them are into the market, yes, but there are also few of them which die. That's the reality. That there was no real application at the moment. So, but because we are in Debau, we are very close to the industry, so we always try to apply this innovation. And now you see the problem of timber engineering, the diversity. I mean, you have so many ideas, so many products, so many innovative things, then the architect say, come on, what I should choose? But it's on one side amazing, because it's good to have so many solutions. But maybe in the future we have to go to some standardization, reducing complexity. I learn it's important. At the end, it's also a question to be economical. And but each company wants to have a speciality just to be unique. This kind of it's a little the characterization at the moment of the timber industry. But when I say that in Switzerland we have the best company, I really think for timber together with Austria, south of Germany, you have really the best knowledge and the best company. Maybe we can say the best education. We have all the ingredients, and we have investors who are happy also to maybe do something different.
I might ask one more question, unless there's a question in the audience. But I mean, feel free to also ask at the apero. So for a final question, I might ask about your involvement with supporting the codes and standards with respect to timber structure. So you even mentioned that the limit is now, I mean, there isn't a specific limit for height, which was previously constrained. So can you share a bit about how your research influenced the development of the codes and vice versa?
Yes, with pleasure, because actually we are sometimes always complaining about the code. On the other side, without code, you cannot build. That's the reality. In some countries, the problem, like Germany, is that the code is a law, so you can only build according to the code. In Switzerland, we are much more liberal. We do what we want. In all these projects, we are not doing based on the code. But really, our engagement in the standard is because at the end, putting this into the code is really improving the application and so on. So we still need liberal code, but we want to implement as much as possible. Even if in Switzerland we are very liberal, but in Germany, in other countries, this is really the problem that you cannot do because it's not in the code.
This is exactly why I ask, because I think that it's also an enabler for others to adopt that don't have the expertise and the lab support that you have at ETH.
But we want to still remain liberal in Switzerland, which is not so straightforward. But we will. I mean, the structure system used in SWAT is a tall building. It was never used. It's the first time. You cannot do this in Germany. You cannot do. Nobody will allow you to build a SWAT in Germany. No, maybe Zustimmung in Einzelzufall, yes, but good luck. Yeah, it's so complicated. And in Switzerland, the architect engineering, and we are doing the test. We say it works. Let's do.
Thank you very much for your talk and for your time. And we would like to share a little thank you from our side.
Thank you.
And please join us for an apéro afterwards.
Thank you.